Hi all, today we are going to discuss about three-phase half-wave control rectifier. In the last class we have seen the case of diode or uncontrolled rectifier where the diode will be automatically on and automatically off. We cannot control at what instant to what instant it should conduct. Whereas in the case of controlled rectifier, because we use the thyristors, we can, by controlling the firing angle, we can easily control the from which duration to which duration each thyristor will conduct, and hence we can control the output voltage and the current. So let us take the case of alpha is equal to 0 or the firing angle is equal to 0, and then we will proceed further. So first I am taking for firing angle is equal to 0. Firing angle is equal to 0 means whenever a particular thyristor is forward biased, automatically it will start conducting. That means it is just like equivalent to the diode rectifier. So how it will happen, you can see here. So at any instant, so A is connected to the anode of thyristor T1, B connected to anode of T2, and C connected to anode of thyristor T3, and the second side is connected through the load to your neutral point. So now whichever anode is positive with respect to the cathode or the second side, so obviously that will be forward bias and start conducting. So out of this A, B and C, whichever is having the more value, because that will get forward biased and conduct to the output. So if you are starting each by one by one waveform, let us try to analyze. So if you are starting the voltage waveform of VA at omega t is equal to 0, it is 0, and it will start gradually increasing, reach maximum at 90 degrees, and again gradually decrease, become 0 at 180 degrees, and so on it will continue. So now coming to the waveform VB. So VB will be lagging behind the voltage wave A by 120 degrees. That means at this instant it is equal to 120 degrees. At 120 degrees it is 0, and 120 minus 90, at this instant it will be maximum value, and again at this instant it is some negative value. So now coming to the value of C, VC is lagging behind the VA by 240 degrees. So at 240 degrees it will be equal to 0, and here also it is 0. So now let us try to divide these timings also. So if you are dividing these timings, at 90 degrees VA becomes positive, and this VA becomes greater than VB and VC from 30 degrees. So this instant is 30 degrees, and this will be at 60 degrees. At 60 degrees VC becomes 0, and from 30 degrees onwards VA become positive, and 90 degrees VA is positive, and this value is, this is 90. Again at 30 this will become 120. Again at 30 degrees, 120 plus 30 will be 150 degrees. At 150 degrees VA will be equal to VB, or we can tell the value of this VC will be negative maximum. So again 150 plus 30, that is 180 degrees, this will be there. Or we can tell that these blocks I can divide as 30 degrees like this. So by default, if alpha is equal to 0, so thyristor T1 will start conducting from omega t is equal to pi by 6. So it will start conducting from this instant. So I have represented this here. T1 start conducting from 30 degrees to, it will conduct for a duration of 120 degrees. That means it will conduct from 30 degrees to 150 degrees. After this 150 degrees, you can see VA is less than the value of VB, as VB is more than the remaining two voltages. So thyristor T2 will be forward biased, and the voltage across thyristor T1 will be, this side VA is connected, this side because B is conducting now, this side it is VB. So voltage across thyristor 1 will be equal to VA minus VB. So VA minus VB, as VB is positive and VA is less than VB. So after this angle, so VA minus VB will be negative, so thyristor T1 will turn off, it is reverse biased. So thyristor T2 will conduct again for 120 degrees. After that you can see the value of this VC is becoming positive or greater than the remaining two. That's why thyristor T2 will conduct, then followed by again T1, because this is VA. Or we can tell that when alpha is equal to 0, the output waveform will be like this. Initially VC up to 30 degrees, from 30 degrees to 150 degrees, that means for 120 degrees duration VA will conduct, then again for 120 degrees VB will conduct, again for 120 degrees VC will conduct. Or we can tell that out of 360 degrees, each thyristor is conducting for a duration of 120 degrees. Each is conducting for a duration of 120 degrees. So let us take the case if alpha is greater than 0. So if alpha is greater than 0, actually the value of Vc should stop conducting at this instant. Agree with me? So after this Va should conduct. So now instead of firing at alpha is equal to 0, we are firing at a non-zero value. That means let us assume I am firing the value of the thyristor at this instant. So I am firing at this instant. This is alpha. So thyristor 1 is fired at an instant of alpha from this reference value. Getting it? So from this instant only Va will conduct. So up to this instant, which one is conducting? Previously as Vc is conducting or coming at your output, that will continue until the Va is fired. So you can see here that Vc is flowing until Va is fired, and Va start conducting, or the thyristor 1 start conducting at an angle of 30 degrees plus alpha. So 30 plus alpha onwards it will conduct, and again at the instant of again here after the angle of alpha, this is because actually Vb should start conducting from here, but instead of here again I am firing my thyristor T2, again it is lagging by an angle of alpha. So Vb is conducting from here, that means Va is conducting up to this instant. So agree with me? Similar is the case the Vc, by increasing the firing angle, so the remaining, because total 120 degrees conduction for each thyristor is fixed. Only thing is the from which instant to which instant it is conducting, only that is shifted by changing the value of alpha. Let us assume I have increased my firing angle greater than 30 degrees. So what will happen? So as you are increasing the value of the firing angle, let us assume it is alpha is equal to 0. So it is this instant will be at alpha is equal to 30 degrees. So up to alpha is equal to 30 degrees. So here up to here Vc is conducting, then Va will come. So at 30 degrees it is the critical value. So if you are increasing greater than 30 degrees, what happens? At omega t is equal to 60 degrees, so automatically the thyristor 3 will stop conducting, because after this the voltage become negative, so it get reverse biased, because it is pure resistive load, it will stop conducting, and when the thyristor 1 is fired again, then it will start conducting again. Again at 180 degrees thyristor T1 will turn off, because at 180 degrees you can see Va is becoming negative, because negative voltage cannot be there for resistive load. So it will stop here, because thyristor will stop conducting when it is reverse biased. Again after some instant, whenever the firing angle is fired, then it will start conducting. That means we can tell that if the firing angle is greater than 30 degrees, there will be some duration for which none of the thyristors are conducting. None of the thyristors are conducting, so no SCR conducts for this much duration. Or we can tell that the duration for which the thyristors are conducting is decreased now. It is not equal to 120 degrees, it will be less than that. So let us try to analyze these things. So first I am starting with alpha is less than 30 degrees. So we know that it is a periodic waveform, it is repeating after every 120 degrees, right? So 120 degrees is nothing but 2 by 3 times of 180 degrees. So 2 pi by 3 duration, integration from alpha plus 30 degrees to alpha plus 150 degrees. So up to that much duration they will conduct. So Vmp sine omega t d omega t. So if you are substituting this, you will get it as 3 root 3 by 2 pi into Vmp. Vmp is the maximum value of the phase voltage cos alpha. So depending on the value of the alpha, the magnitude will goes on changing. As the value of alpha is increasing, automatically average voltage will goes on decreasing. So now this can be written in terms of the line voltage, because we know line voltage is equal to root 3 times of the phase voltage. So maximum value of the line voltage I am representing by VML. So this will be equal to root 3 times of VMP will be equal to VML. So this will be 3 times of VML by 2 pi into cos alpha. Similarly, RMS value also you can calculate. Only thing is I have to do square and to the power of 1 by 2. So when you calculate it, you will get this answer in this way. So now RMS value of the output current will be equal to RMS value of output voltage divided by resistance, because it is a resistive load. Similarly, I can tell the average value of the output current. The value of the output current I0 will be equal to V0 divided by R. That is my average current that is coming at your output. So now for alpha greater than 30 degrees. So for alpha greater than 30 degrees, there is some non-conduction region also. So that's why the thyristor T1 in our example is conducting from 30 plus alpha to 180 degrees. Similarly, thyristor T2 conducts from 150 plus alpha to, when that B phase is becoming equal to 0, it becomes 0 at 300 degrees. So up to 300 degrees and so on. Similar is the case for C phase. Or otherwise we can tell that each thyristor is conducting for a duration of, it is conducting from 30 plus alpha to 180 degrees. You agree with me? So we have to subtract 180 minus 30 plus alpha. So 180 minus 30 is 150. This is 150 minus alpha degrees only. So if you are going on increasing the value of the alpha, the duration for which the SCR conducts will goes on decreasing. Agree with me? When alpha is equal to 150 degrees, the output voltage will be equal to 0. No output voltage will come. So maximum possible value of alpha will be equal to 150 degrees only for the case of resistive load, because a negative voltage is not possible for resistive load. So now coming to the value of the V0. So out of 120 degrees, it is only conducting from alpha plus pi by 6 to only pi, up to 180 only it is conducting. So I have substituted, you will get your answer as 3 VMP divided by 2 pi into 1 plus cos of alpha plus 30 degrees. Similarly, RMS value also I can calculate. So this will be the RMS value. So how to make the continuous conduction? So how to break the problem of non-conduction region even for the alpha is greater than 30 degrees? That is possible by connecting an inductor in series with a resistor, or for the case of RL load. In the case of RL load, I am taking if the inductance is very high, it will not allow the change in the current. So that's why we can take your output current as nearly equal to constant, that is equal to I0. So now depending on when you are firing it, so the particular thyristor will go on conducting until the next thyristor will start conducting. Let us take for example, initially the thyristor 3 is conducting. So thyristor 3 is conducting. So at this instant, that means 30 plus alpha, because this value is 30, right? So 30 plus alpha, I have fired the thyristor T1. So up to that instant it will go on conducting. So if the alpha is greater than 30 degrees, there can be negative voltage also. The voltage can even go to negative. So that's why the waveform will be like this. So again VA is conducting. So again it will conduct until the thyristor T2 is triggered. So negative voltage also can come. So same thing is the case for this one and so on. So now coming to the current supplied by the each thyristor. So as your output voltage is nearly constant, which is supplied by two thyristors. So thyristor T1 is conducting from 30 plus alpha. This is equal to 30 degrees, right? 30 plus alpha, from that instant it will conduct for a duration of 120 degrees. Then after that thyristor T2 will take over the current. It will conduct for 120 degrees. Then thyristor T3 will take over. It will conduct for 120 degrees. So now coming to voltage across the thyristor 1. So what is the voltage across the thyristor 1? You can observe from here, voltage across thyristor 1 will be equal to, I can write my value of VT1 is VA, because voltage at this side, minus voltage in the output side, whatever is the V0 is there, that is applying here. So this is VA minus V0. Agree with me? So now let us see. So I am taking the, so at this angle, so you can see here initially what is the, that is conducting, VC is conducting. So your output voltage will be equal to VC. So voltage across the thyristor will be equal to VA minus VC. So this is VA and the value of VC is this one. So VA minus EC, initially it is negative. So here at this instant VA is equal to VB. So VA is equal to VC. So automatically this is my value VC, right? So VA is equal to VC. So it becomes 0. And gradually VA is positive, VC is decreasing. So that's why, so voltage across the thyristor is increasing until we do the firing. So let us assume we have fired the thyristor at this instant. So after this instant, the thyristor is started conducting. So automatically output voltage will be equal to VA and voltage across thyristor is equal to 0. So again at this instant, thyristor T2 is fired. When the thyristor T2 is fired, what is your output voltage? Output voltage will be equal to VB. So voltage across the thyristor 1 will be equal to VA minus VB. So what is the value of VA? So this is my VA, which is negative, minus VB. Minus VB means whatever VB is there, reverse the waveform and add to this. So it is becoming more negative. That's why it is increased to negative value. So after this you go on subtracting VA minus VB. So you can see this is my VA, it is going on increasing, but VB is going on decreasing. Okay, and up to certain extent, even though because this is increasing and this is decreasing, and it will go on increasing up to some peak value. So after that it will goes on decreasing. Again at this instant the thyristor T3 is triggered. So now your output voltage is changed from VB to VC. So now the voltage across the thyristor will be VA minus VC. So what is my VA? So this is my value of VA. This is my value of VA, which is negative, VA minus VC. This is the maximum value, so that's why it reached the maximum value. Then it will gradually goes on decreasing. So that means we can tell that voltage across a thyristor is nothing but the line voltage or voltage between two phases. So what will be the maximum value it can go up to? It can go up to root 3 times of VMP. It can go up to root 3 times of VNP. So I can tell that peak inverse voltage across each thyristor will be root 3 times of the phase value. It will go up to the line voltage. I hope this is clear up to now. So let us try to derive the equation for the output voltage. So out of 2 pi by 3, that means 120 degrees, it is conducting for 120 degrees from alpha plus pi by 6 to alpha plus 5 pi by 6. That means alpha plus 30 to alpha plus 150 depending on the value of alpha. So if you substitute it, you will get it as 3 root 3 by 2 pi into VMP into cos alpha. So here you can observe that as the value of cos alpha is increasing, automatically output voltage goes on decreasing, and when alpha is equal to 90 degrees, your output voltage will be equal to 0 because cos 90 is equal to 0. Agree with me? So if the alpha is greater than 90 degrees, what will happen? V0 will become negative because cos 90 plus theta, this will become minus of. So this will become negative for the angle greater than 90 degrees. So same thing I have mentioned here, for alpha greater than 90 degrees, V0 will be negative. So as the output current is positive but V0 is negative, V0 multiplied by I0 will be negative power. So what is the meaning of this? Instead of taking the power, it will start supplying the current back. So theoretically it is possible, but practically when the voltage is negative, how the current will be positive? It is not possible. So it is possible only when there is RLE load. That means there is some voltage source in your load, then only the current can be maintained positive even though the output voltage is negative. So how we can get it? We have to use an RLE load. So in the case of RLE load, it should be like this. This is my R, this is my L, and the terminals of E should be reversed. So E should have negative and plus terminal like this. So in that case, automatically because E will force the current to pass in this direction, so I0 will be positive even though V0 will be negative. So this thing we have already seen for single phase full converter with RLE load. So line commutated inverter, I have taught one topic previously. You can please refer to that lecture. Okay, now I am proceeding further. So proceeding for the RMS value of the output voltage, again same procedure we can calculate. I am not going into detail because you already acquainted, because we have already taught so many lectures. You know how to make the calculations. Only you should know that what value it is conducting and how to analyze it. So now coming to the average value of output current will be equal to V0 divided by R, and the average value of the current supplied from your source. So current supplied from your source, we can see here each thyristor is conducting only for 120 degrees out of total 360 degrees. So out of total 360 degrees, so it is conducting only for 120 degrees of a magnitude of I0. So average value will be equal to I0 divided by 3. So now coming to the RMS value will be again out of 360 degrees, it is conducting for 120 degrees. So I have to take as 1 by 2 pi integration from that. For a duration of 120 degrees, you have to take I0 square d omega t. So when you substitute it, you will get it as I0 divided by root 3. Now coming for the RL load with the freewheeling diode. So in the case of RL load, we have observed that the voltage is going to the negative value. You can see here voltage is having both positive value as well as a negative value. Because of this negative component, automatically average value of the output voltage is decreased, because the purpose of the converter is I should get the maximum DC output value, output power. That means DC output power means I should get maximum possible average output voltage and maximum possible average output current. So that negative voltage should be removed so that my average output voltage will improve. And second one, I can improve my power factor also. So in order to understand this more clearly, you can refer to the case of the freewheeling diode case. I have explained the single phase semi converter with freewheeling diode. So how it is going to improve the power factor and other things. So you can please refer to there. Okay, let me proceed for this one. So 3 thyristors are there, 1 freewheeling diode is connected. So how this will operate? Again it is RL load for alpha less than 30 degrees. If alpha is less than 30 degrees, you can see here this C is conducting up to the value of alpha. So if alpha is less than 30 degrees, the output voltage will be continuous, negative value doesn't come. So this freewheeling diode doesn't play any role. But if alpha is greater than 30 degrees, as the output voltage is trying to go to negative, whenever the output voltage, like for example VC is conducting here, so thyristor 3 is conducting, so here after this instant it is going negative. So whenever it goes negative, because you can see this is nothing but the cathode of this diode is becoming negative with respect to neutral. When this point is becoming negative, the freewheeling diode will get forward biased. When the freewheeling diode get forward biased, so the output current will be bypassed through this freewheeling diode. So it will be forward biased, it will start bypassing through this. So your output voltage will be, because under forward bias condition it will act as a closed switch, so output voltage will become equal to 0. You can see the output voltage is 0, and during this time the current is conducted by the freewheeling diode. Again same thing, now A is conducting, and whenever A becomes 0, so during that time, that means when A try to go to the negative value, from that instant to the instant when VB, that means thyristor 2 is fired, for that much duration freewheeling diode will conduct again. So in this way it will continue. So same thing I have explained here. So for alpha greater than 30 degrees, I am taking the example of 60 degrees. Let us take for example. At omega t is equal to pi plus, that means 180 degrees plus. 180 degrees means this is the pi, right? So 180 degrees plus. So freewheeling diode, because VA is becoming, because VA has reached 0, it is going to negative. So automatically the freewheeling diode is forward biased and conducts from pi to 150 plus alpha. That means the instant when the thyristor T2 is triggered. Getting it? So each SCR conducts for a duration of, from which duration to which duration it is conducting? It is conducting up to only 180 degrees. So 180 minus, it is fired at an instant of 30 plus alpha, thyristor T1. So 180 minus 30 plus alpha. So this will be equal to 150 minus alpha. So each SCR is conducting for 150 minus alpha degrees. So how much duration the freewheeling diode will conduct? So freewheeling diode will conduct for the remaining duration, that is equal to alpha minus 30 degrees. This will conduct for a duration of alpha minus 30 degrees. So you can see here, so at this instant at omega t is equal to pi, it stopped conducting, and it will again start conducting when the B is fired. When B is fired, 150 plus alpha. So for how much duration freewheeling diode is conducting? Freewheeling diode is conducting for 150 plus alpha minus 180. So 150 plus alpha minus 180 will be equal to alpha minus 30. That way this freewheeling diode conduction came. I am repeating once again. So this thyristor T2 is triggered at the instant of 150 plus alpha, and from the instant of 180 degrees output voltage is 0. So for how much duration freewheeling diode is conducting? Freewheeling diode is conducting for a duration of, this is 150 plus alpha, this is 180. So 150 plus alpha minus 180, that will be equal to alpha minus 30 degrees. So same thing I have mentioned here. So freewheeling diode, you can see in one cycle freewheeling diode is conducting for 3 times. Freewheeling diode is conducting 3 times, and each time for a duration of alpha minus 30 degrees, and the current passed by each thyristor will be 150 minus alpha. 150 minus alpha. Getting it? So now coming to the output voltage, average output voltage will be 1 by 120 degrees is the duration. Out of that it is coming from, conducting from alpha plus pi by 6 to pi only. So automatically because of this, the average value of the output voltage is improved when compared to this previous case. So now the RMS value of the output voltage equation will be this one. RMS value of output voltage will decrease, but my major concern is the average value of the output, because I want the converter, it should conduct to pure DC. So now average thyristor current. So thyristor is conducting for a duration of 5 pi by 6 minus alpha out of 2 pi. So that's why it will be I naught into 5 pi by 6 minus alpha divided by 2 pi, and RMS value will be I naught multiplied by 5 pi by 6 minus alpha by 2 pi whole to the power of 1 by 2. So now coming to the freewheeling diode, the freewheeling diode is conducting for a duration of alpha minus 30 degrees, and how many pulses are coming? 3 pulses are coming in 360 degrees, or for each pulse, that means duration between the pulses will be equal to 120 degrees. So that's why it is 2 pi by 3, I have to take the reference. So I naught into alpha minus 30 divided by 2 pi by 3. And the RMS value again same thing, I naught into 3 by 2 pi into alpha minus 30 degrees whole to the power of 1 by 2. So till now we have discussed about half wave control rectifier. So first we have started with the R load, and we have seen what the R load up to the angle of 30 degrees the conduction will be normal. If the value is greater than 30 degrees, there will be discontinuous conduction mode, that is a disadvantage. And if the value of alpha is greater than 150 degrees, no output voltage will come. So in the case of RL load, we have seen the negative voltage also can come, so it will start conducting. And when the value of alpha is greater than 90 degrees, we have seen that it can act as a line commutated inverter, provided there is a voltage source also in the load, that is RLE load with E terminals reversed. And in order to improve your output performance, that means in order to increase your average output voltage and improve the power factor, so the better option is go for a freewheeling diode. So by connecting the freewheeling diode, we have seen that output voltage never go to negative, so automatically average output voltage is improved. And the second one, the energy stored in the inductor will be supplying when all the thyristors are off. For this duration, freewheeling diode will discharge the energy that is stored in the inductor. So in that way it will conduct. So we have seen how to calculate the formulas and other things. I hope that single phase half control converter is completely clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.